This video will show some common machining methods for polymer matrix composites. We'll be covering conventional machining, such as those using drill presses and milling machines, as well as water jet machining. We'll emphasize the major differences between machining of composites versus machining of metals, and the steps that you could take to avoid damaging composite parts during machining. The most common types of damage that occur during machining of composites are delamination and fiber splitting. I will use drilling operation as an example here. In a drilling operation, delamination can occur on both sides of the composite laminate. If you look at the design of a drill bit, which has a spiral flute and a rake angle, when the drill bit enters the part, the drill bit creates an auger action which pulls the laminate up, which may create delamination on the first few plies of the laminate. Materials that are removed in the drilling operation, if not properly removed from the whole area, could contribute to delamination and fiber splitting also. This is particularly true if the drill bit is dull. And when the drill bit exits the part, it may push the last few plies out of the laminate and create delamination on the back side. One of the things that we can do to avoid delamination is to have sacrificial laminates on both sides of the part. We will have to apply some amount of pressure on the sacrificial laminates during the drilling operation. This will protect both sides of our part. If delamination occurs, it will occur on the sacrificial laminates and not on our composite part. Other things that we could do to avoid delamination is, in general, faster spindle speed, slower feed rate, and very sharp and hard cutting tools. We will cover some basic concepts of cutting tool design later. This is showing a drilling operation on a composite laminate. Machining coolant is running to keep the part cool and to remove machining debris. There is a sacrificial fiberglass laminate on the composite laminate. The fiberglass laminate will prevent delamination on the composite laminate. In this case, it will also prevent the clamp from pinching and damaging the composite. The drill bit is a carbide drill bit and is mounted on a chuck. It is important to make sure that you are using a high quality chuck that does not wiggle, or if you are drilling by hand, that you have a very steady hand. Wiggling may cause delamination and oversized hole. This particular hole requires very tight tolerance, so we are using a carbide reamer to achieve the final hole dimension. The reamer will also remove small amount of delamination that may have been created during the drilling operation. Note that the reamer has a straight flute, so it is less likely to create delamination on entry. And we are not removing a lot of material in the reaming operation, so we don't really need the flute to have any spiral. Let's spend some time to talk about drill bit design. This is an area of intense research, so some of the things that I'm about to share may be controversial or become obsolete in time to come. The bottom picture shows a drill bit that is not suited for drilling composites. The insert has a very wide drill point, which is likely to create delamination. In order to prevent delamination, a smaller drill point is usually preferred. Some drill bits that are designed specifically for composites have dual drill point angles. The outer angle is smaller to prevent delamination around the hole. The fast flute spiral will also make this drill bit more prone to creating delamination because the flute will create an augering action. At the cutting edge of this drill bit is actually a PCD insert, and its rake angle is 90 degrees, which is not very sharp. The top picture shows a specifically designed drill bit. The rounded drill point is designed to prevent delamination. The rounded drill point is essentially a variable and continuously decreasing drill point angle. The slow spiral will create less augering effect. There are some specifically designed drill bits that have straight flutes, but straight fluted drill bits are poor at removing machining debris away from the hole, so unless you have machining coolant and vacuum running to help remove the debris, straight fluted drill bits may not be preferred. Let's take some time to look at cutting tool materials. Since composites are fairly hard and abrasive, the cutting tool materials must be very hard. High-speed steel or even cobalt are usually not hard enough to machine composites. The most commonly used cutting tool materials are tungsten carbide and diamond abrasive. On the left is a tungsten carbide end mill. Tungsten carbide tool will provide a smooth and close tolerance machine surface. This tungsten carbide tool has been coated with diamond. The darker color here is characteristic of a diamond coating. Diamond-coated carbide tools will generally outlast regular carbide tools, but the cost benefit is debatable because diamond-coated carbide tools are much more expensive than regular carbide tools. At the center is a diamond abrasive grinding bit. Diamond abrasive tools are generally more durable than carbide tools or even diamond-coated carbide tools. The diamond abrasive particles are bonded to the tool using electroplating or brazing process. But the diamond abrasive tools have a major disadvantage when compared to carbide tools. They will create a rather rough machine surface and tolerance is not as good as carbide tools. The grinding bit on the right is sometimes used for scuff sanding of composite laminates. The main disadvantage of grinding bits is that they will wear much quicker than diamond abrasive bits. The abrasive particles and binder material that are dislodged from the bit may adhere to the composite part, resulting in potential contamination problem if the machine surface is to be adhesively bonded later. It is important to make sure that the grinding bit and the subsequent surface preparation and bonding operations are qualified and will produce good and durable structural bond. This is an example of a poorly drilled hole in a composite laminate made of fabric material foam. There is usually bulging around the hole, which can occur on both sides of the laminate. This is an example of a poorly drilled hole in a composite laminate made of unidirectional plies. In general, unidirectional plies are more prone to delamination and fiber splitting than fabric material foam. The delamination area is sometimes dependent on the fiber direction of the outer ply. In this case, the fiber of the outer ply is running vertically, so the delamination is primarily located at the top and bottom areas of the hole. Delamination in unidirectional laminates are usually accompanied by fiber splitting around the hole. Most conventional machining methods such as grinding and milling can be used successfully on composites. The machining parameters such as feed rate, cutting tool speed may require some trial and error. In general, the feed rate is slower, cutting tool speed is faster, and material removal rate is slower when compared with machining of metals. Water jet machining is becoming very popular for composites because it is fast, can be automated, can cut through very thick sections, and produces less airborne dust when compared with conventional machining methods. Let's start by covering some basic terminologies. The cutting edge, in this case it is a water jet, is produced at the nozzle. The water jet pressure is usually set at between 40,000 to 60,000 psi. Water is usually mixed with abrasive media such as garnet because cutting by water alone will cause delamination. The parts are supported by slats, which are vertically oriented metal plates. Clamps are usually used to secure composite parts during machining process. Most machines are computer controlled, so it can follow complex tool paths at very high precision. This is showing the water jet machining a piece of 3/8 inch thick aluminum. This is showing the water jet machining a piece of composite laminate. Water jet can machine very thick composite parts. This is a 200 ply, 1 inch thick composite laminate. With proper settings, the water jet was able to produce very clean and straight cuts. Let's look at some common defects that are produced by water jet machining. Sometimes, the curve may be tapered and the machine surface may have striation marks. Frosting may be visible on the composite surface. Frosting is surface abrasion usually produced where the material is pierced or where water jet bounces back from the slats. Frosting is usually a cosmetic issue only, although severe cases of frosting could result in the removal of the outer plies. Delamination is perhaps the most detrimental form of defect. Delamination usually occurs when the flow of abrasive media, garnet, is disrupted, since machining by water alone without abrasive media will produce delamination.